Hello and welcome to a short presentation of my thesis. My name is Manuel Schrick, and in my thesis I introduce an algorithm that generates layouts for connector and component models, specifically for textual connector and component models written in embedded Monty-Arc. In this video I will give at first a short overview about the basic steps of the algorithm, and after that I will go into more detail for every single step. So we start with the textual model itself, and the first step is to extract the underlying graph of the model. And once we have that, we find paths inside this graph, and we lay out these paths in a table where each node has its own column. And the next step is to find an vertical ordering of these paths that corresponds to a visually appealing layout. And after that we can compress the whole table a little bit, and then we are basically ready to assign the coordinates to the components and the connectors and generate the final output files. At last I want to talk a little bit about temporary nodes. These are nodes that really do not exist in the model itself, but we add them to create vertical lines in the final layout. So the first step was to extract the underlying graph out of the textual model, and we do this pretty straightforward by creating one node for each component that is in the model, and one edge for each connection in the model. The exception of this rule is the enclosing component, which gets two nodes assigned, one for all of the incoming ports and one for all of the outgoing ports. After we build up this graph structure, the next step is to find paths in this graph, where a path is a sequence of connected nodes and all the connections go in the same direction. And we lay out these paths in a table where all connections go from left to right. One rule we have for these paths is that if they share a node or two, then this node has to be the start or the end of one of these paths. And when we add these paths to the table, we create one column for each node. Another thing that we do here is that when there are multiple connections between two nodes, like A and D in this example, we only create one path, but we keep in mind the actual number of connections between these nodes. And in this example, there's a circle from A to C and back to A, and we will need temporary nodes for that, so I will come back to that later, and I will not talk about this now. So after we build this table, the next step is to find an ordering of the paths in the table that corresponds to a visually appealing layout, and we do this by using simulated annealing, which is a heuristic that compares two intermediate solutions of the problem and uses a fitness function to compare these solutions. And in our case, the fitness function takes the size of each node and the number of connections that go through each node. In this example, if you look at the left graph, there is a connection from A to D, and the node C goes from column 1, from row 1 to row 3. So the connection from A to D goes through the component C, which would be included negatively in the fitness function. And we calculate a candidate solution or a candidate ordering by just swapping the places of two randomly picked paths. So after we found a good ordering of the paths in the table, We can shrink the whole layout a bit, and we do that in 2 steps. The first step is by vertically scanning through all the paths in the table and merging 2 paths whenever this is possible. So in this example, we can merge the lowest 2 paths because there is no information that we lose by moving the connection from D to minus up into the path above that. And in the second step, we do the same thing basically horizontally by scanning through all the nodes and checking if we can move the respective node to the left. And if this is the case, then we do so. In this example, we can move node D 2 columns to the left, and by doing so, between C and minus there is an empty column that we can remove from the table. The next step is to assign the coordinates to the components and the connectors, but before we do that, we have to add the missing connections from A to D back into the layout. And we do this by just simply checking the rows above the first connection from A to D and insert the connections wherever possible. And if there's no line or no row with enough space for this connection, then we will just add new rows. And the coordinates of the components then look like the coordinates of the table cells the nodes are in. So if you take a look at node A or component A, it goes from the top of the first row to the bottom of the last row, and from the left of the second column to the left of to the right of the second column. And the same thing we do for all the other nodes, except for the enclosing component, which will just take up the whole first column and the whole last column, and thus surrounds all of the internal components. The ports will be placed in the vertical center of the respective row of the connection, and on the left or on the right edge of the respective components, depending on whether this is an input port or an output port. And the connections will then connect the vertical centers of the input port and the output port. So now that we have calculated all the coordinates of the elements in the layout, we can generate the final output files. And for that we use free marker templates, and we create SVG vector graphics and embed these into HTML files, which has the advantage that we can open these and view these files basically from every web browser that we choose. So up until now we only used horizontal lines for the connections, but if we have, for example, back connections, like in this model, there's one connection going from C back to A, then we need vertical line segments to draw these connections. And as I said earlier, we use temporary nodes for this. And in the step where we build the paths, or we look for the paths in the graph, and we realize that we reached a cycle in the graph, then we will add not only the 2 nodes A and C, but also two temporary nodes, A prime and C prime, where A is on the left, A prime is on the left of A, and C prime is on the right of C, and A prime is connected to A and C prime, and C is connected to C. And in the final step, where we assign the coordinates to the connectors, we replace these temporary nodes by vertical lines, and this allows us to draw connections that not only go horizontal but also have vertical line segments in them. A second advantage that this approach has is that we can include these temporary nodes into the heuristic itself, which means that we can not only use the size of the components as a measure of aesthetics of the layout, but we can also use the length of these connectors, as the size of the temporary nodes directly corresponds to the length of the connector going back.